Excellent. All right, folks, I will begin. As Jacqueline kindly mentioned, Kyle Hanson, I do work for Suncor. I'm not here promoting any of their products. As you'll find as we go through here, there's really not a lot differentiating between us and our competitors in terms of actual fuel products, but happy to be here. Been here for, been with Suncor for a little while now, specialized in the kind of the refining side of things, laboratory analysis and product specifications. So I always like to start these presentations with an overview of kind of the refining process, a very brief overview because it is a lot more complicated than this, obviously. But so essentially what we do to produce the fuel, we heat the crude up quite a bit, and it goes into what is called a distillation tower here. We essentially boil the fuel. The lighter components go to the top where we have our LPGs, propanes, butanes, things like that. And we have our naphtha cuts that essentially all goes into gasoline, kerosene into jet fuel. Some of this stuff does go into gasoline. There is significant overlap amongst these cuts here. But the take home here is basically some of these larger molecules at the bottom, they'll get broken down and brought up into the gasoline stream and the diesel stream. So just basically trying to squeeze every cent out of crude molecules. The refining sector here, I did want to overlay this with kind of our pipeline distribution network, but the picture does get overly complicated once you start adding the distribution streams over this. So kind of what I wanted to emphasize here is that there are a couple of kind of production hubs in Canada. One is centered around Sarnia down here in the east. And then you'll see all of these four guys here up in Edmonton. So essentially Edmonton and Sarnia are production hubs. We do have the big one, Irving, out east. But as far as kind of the big three, Suncor, Shell, Imperial, we're kind of focused in the Sarnia and Edmonton area. One thing I should mention, there is a large terminal out in Vancouver called the Products Terminal, shared with IOL and Suncor. It's more or less a terminal, but it's kind of a quasi refinery because it does have some processing capabilities. Another thing to take out of this is that current refining capacity is outpacing demand. So we do have to export some of this fuel, some of these finished fuels, I should say. Downstream, the fuel distribution network, it is quite complicated, but this is a nice simplification here. So obviously fuel quality begins with the crude type, but the specifications actually begin at the refinery. Storage is quite large at a refinery, so storage will drop as we go through this process from the refinery to storage terminal down to retail. And another thing to take out of this is that there are standards and specifications for basically every single step in this process. We have our refining specifications and regulations. We also have storage specs, specifications for truck, rail, and marine. We have specifications for pipelines. We have specifications at terminals and bulk plants. Specifications do apply at retail. We don't do a lot of testing there, obviously. We do monitor tanks for water and things like that, but most of the testing is happening at the refinery and terminal level, but we are monitoring the fuel every step of the way. One thing to kind of note here is some things, some of the fuels produced at the refinery, some of the parameters, I should say, we do overcompensate and try to anticipate degradation of certain properties. A couple that come to mind are conductivity of diesel fuel. That basically drops as the fuel is handled. So what we'll do at the refinery, we will overdose. The minimum specification is like 100 picosiemens per meter at end of use. So at the refinery, we'll put it up to 300, sometimes up to 600, just in anticipation of what the fuel is going to be like at the retail end or the end user, or for the end user, I should say. Another one we monitor is sulfur in diesel. A lot of these transportation networks, they do share common pipage and tankage with gasoline sometimes. So Gasoline has higher sulfur standards, so we are quite sensitive to sulfur pickup on diesel, because diesel, as you will see later in this presentation, has very tight specifications in terms of sulfur. So we'll start with gasoline here. It's a light energy dense fuel used mainly in internal combustion engines. As most of you know, there are two sets of standards in accordance with CGSB. So before we go forward, the CGSB, they're basically the board that sets the standards and specifications for gasoline. A little bit different than regulations, whereas regulations are coming from the government. The specification, this is a standards board. There are members of government, people in industry, subject matter experts. It's basically a board that gets together and meets and sets these standards. The CGSB standards, we do, they're not law in most places, but we do have agreements with our competitors, frenemies, as well as other contracts and things like that. So we do have to meet these specifications, even though they're not law in some areas. There are a couple of areas, Quebec and BC, CGSB is mandated law. And in Ontario and Manitoba, once we put renewable fuel in, then it becomes subject to law. So there's two sets of standards for gasoline. CGSB 3.5, that's automotive gasoline. So that's our conventional gasoline, no ethanol. This is the stuff your parents and grandparents would have used, sans lead, let's say. The next one there, CGSB 3.511, so oxygenated automotive gasoline containing ethanol. So that's your standard for gasoline containing ethanol. The standards do overlap quite a bit, but there are some parameters that need to be adjusted for with the ethanol. I like this little pie graph here because I should have put it next to diesel to kind of illustrate the differences here, but the nature of gasoline, it's not as energy dense as diesel. So it's more suited for lighter pieces of equipment, cars and light trucks, as you can see from this chart here, 96% of use. And recreational boats, things like that make up a small percentage, but those are things you have to think about when you're making these fuels and producing them. Gasoline key properties. The biggest one with gasoline is volatility. It's kind of a generally used term. So it's gasoline, we seasonally adjust it to vary the volatility depending on the season and geographical area. Basically to maintain good drivability in terms of ambient temperatures. The volatility parameters that we worry about are vapor pressure, distillation, and drivability index. Most of you probably know vapor pressure is the volatility of the gasoline. You may hear the term RVP. That's kind of how we roll with vapor pressure in the petroleum industry, but RVP is short for read vapor pressure. It's just a method for us to determine vapor pressure at elevated temperatures. The standard for gasoline measurement is 100 Fahrenheit. A lot of these things are still kind of stuck in the imperial world, but that's 37.8 Celsius. Distillation determines the temperature required to evaporate known portions of material. So we'll just basically boil the product and get the cut points. Okay, at 50% of evaporation, this is the temperature. Drivability index. This is not a commonly known fuel quality parameter, but it is part of the regulations, or sorry, CGSB and some regulations. It's basically a calculation based on the distillation temperatures. It takes into account the entire range. So, refiners aren't cheating in the winter by, sticking some heavy stuff in the back end. So instead of looking at just one distillation cut, it's looking at all of them and providing a calculation, and you get a number. And those are specs based, again, on geography and climate. So why is it important? Well, it's crucial to engine starting, warm up, and smooth running. The relative amounts of low and high boiling components are varied throughout the year. So in general, winter gasolines will have high vapor pressure and high volatility. That gasoline will have a lot of butane in it. That's that's how we control the vapor pressure more or less in the winter, is by adding more butane. So more light components that evaporate easily to give good starting and performance under cold winter conditions. Summer gasolines have a lower vapor pressure and lower volatility to improve performance during warmer weather and to lower emissions as well. So you probably don't notice this stuff in your car too much. Maybe if you filled your car up in summer and let it sit there for 6 months, you might notice something. But where I really notice the gasoline volatility properties is in my my lawnmower and weed whacker motors at the beginning of the year, because they usually have pretty old gasoline sitting in there. And once it loses all of its light ends, and then you lose that volatility, and you lose some of the performance that you would expect out of these. This is a picture of one of my old cars that I used to drive when I was a teen. I always just try to stick this into my slides. Oh, sorry. That is a 86 Pontiac Fiero. Gasoline key properties. So in terms of manufacturing and regulations, we're always worried about volatility, but probably what end users are most familiar with is octane. So it's basically the anti-knock index, or it's a measure of the combustion quality of the gasoline. So the higher the octane number, the more compression that fuel can take before it detonates or explodes, I like to say. I really like this figure here, because it's a good kind of visual of what octane actually means. So you see on the left there that the piston is compressing the air. Nothing is supposed to happen until that spark plug ignites or sends the ignition, or the spark, I should say. That is when an engine is supposed to get that power stroke. So what you see here next to it is spontaneous combustion causing engine knock. So these two conditions on the right are usually caused by the fuel basically exploding or igniting due to pressure. We do not want that in a spark plugged engine. We'll see a bit later what cetane means. Cetane is the exact opposite, so we'll get into that a little bit later. But so you guys probably are not familiar with engine knocking. I am not familiar with the actual physical knocking of an engine, and that's because gasoline engines are basically monitored with a computer now. So you have real-time feedback and really, so a lot of this is it's an illustration of what happens. Again, you're not going to feel this because kind of before computers were introduced, knocking would commonly occur and cause significant engine damage. But most modern engines have sensors to detect this. And so you wouldn't even feel the knocking, because what an engine will do nowadays, they will actually delay the spark, or even delay some of the movement of valves to kind of compensate once it feels engine knocking or power surges. Again, not something you would typically feel in your motor, but these things do happen, and you probably wouldn't want to rely on your computer long-term to adjust the stroking and firing of your engine. So what I'm saying here is you don't want to drive around and thinking it's okay with an 83 octane gasoline that you picked up somewhere. So and there are octane requirements. So below are the actual, this is what most of you are familiar with. These are the numbers on a pump. So your regular 87, mid-grade 89, premium 91. Some retail stations are offering a super premium, or 93. Often you'll see a 94. We'll get into a little bit of that later, and that is due to the ethanol addition. Let's go back here. Someone is probably going to ask me, should I run premium in my car? I would always suggest check your manual. If it suggests it, probably not required. If it says it is required, definitely use it. Gasoline additives. So these are the four main additives. There are some aftermarket ones that some companies try to peddle, but these are, let me back up a little bit. Producers are only allowed to use certain additives, and they have to be qualified, and they have to have science behind them, and they have to be on the EPA list of approved additives and things like that. It's not just, oh, look at this chemical, it helps this, let's use it. No, there's a lot that goes into approving additives for use, especially for the producers. So deposit control additive, designed to keep the entire fuel engine system clean by preventing or removing deposits on metal surfaces. So when you hear the term top tier gasoline, that is essentially referring to the amount of deposit control additive within the fuel. Basically, all major retailers are top tier or top tier qualified. Right now, top tier is actually a moniker you have to pay for the use of the name. So there are providers out there that meet top tier requirements, but it might not say it on the pump, but most of them do. There are some boutique sellers, grocery store chains, things like that may buy gasoline that doesn't have as high a deposit control additives. So there are differences, but there are minimum standards. So you're not going to get a gasoline that doesn't have it, because what we find, if you have a gasoline that does not have a DCA, you're going to have fouling valves probably fairly quickly. Things like to gum up and oxidize. So oxidative stability is the next one. Eliminates free radical chain reactions involved in hydrocarbon oxidation. I couldn't find a better term for that. Essentially, the oxidative stability additives limit oxidation of the fuel. Allows for extended storage. You're gonna have less gumming up of fuel in tanks and pipes and things like that. Corrosion inhibitors. So gasoline in itself, without additives, more often than not, will cause rust to ferrous metals. Essentially, every blend I've been a part of, we've had to use some sort of ferrous corrosion additive to prevent that. It's not just in people's vehicles, it's tanks, it's pipelines, anything gasoline will come into contact with throughout the distribution chain. It does need that protection. And some blends will cause copper and silver corrosion. So there are copper and silver corrosion inhibitors as well. They're a bit different from the ferrous ones, but kind of the same idea applies. Every single, really, I wish I could have got into the nuts and bolts of each fuel here, but gasoline requires corrosion testing to pass before we can sell it. So it's not a nice to have, this is a must have. Up next, red dye, not really a performance additive, but it's used for taxation. So basically off-road fuel, farmer fuel that does contain red dye. It is highly regulated. The concentration must be at 14 ppm minimum. It can be a bit higher, but it has to be a minimum of 14 ppm. And I believe that's to reach a certain color of the fuel. Looking at dyed fuel and clear fuel, you can see there's quite a bit of difference. As a quality advisor, I oversee the quality of our products. But when it comes to dye, if we have a dye issue and it comes to me, I have to take that immediately to our taxation department, because that has regulatory consequences for taxation, and more for that and not much for quality. But it is an additive that is required. Gasoline regulations. There's three big things: environment. They used to be Environment Canada, they're now Environment and Climate Change Canada. The three big things they're worried about are sulfur, vapor pressure volatility, and benzene. So sulfur, Environment and Climate Change Canada gives producers two ways of reporting our sulfur. We can have every single batch below 12 ppm. Or we're allowed to use a pooled average value. So we would be able to have a blend of gasoline up to a hard cap of 80 ppm sulfur, but our overall pooled average must be below 10. Vapor pressure. There are some special provincial regs around the warmer areas of Canada. One being Southern Ontario, another Montreal, and then the lower Fraser Valley, so Vancouver area of BC. What's special about these three areas, they will actually have lower RVP than the rest of Canada during the summer months because it is a little bit warmer. And as if you recall from a few slides ago, you really want to lower RVP in summer or warmer climates. Benzene. So it's another one where you have a couple of choices what you want to do in terms of reporting. So we got a flat limit of 1% or a pooled average of 0.95 and a cap of 1.5. There is another, well, it's related to benzene. It's called the benzene emissions number. It is a crazy calculation. I wouldn't recommend doing it by hand. There's some conditional values in there, but complex calculation involving benzene, aromatics, distillation, vapor pressure, oxygen, and sulfur. So basically, they calculate all of that put that all into an equation, and it spits out a value that's related to the emissions of benzene from a tailpipe. I've seen this, I know the equation quite well, and I still can't make sense of how it comes out to actual benzene emissions in tailpipes, but we do have two sets of hard specs, a 71 in the summer and a 92 in the winter, and they are unitless values. I just kind of wanted to highlight kind of what changing fuel regulations can actually do. So what we have here is a couple of figures from Environment and Climate Change Canada that illustrate kind of what happened during the late 90s when the benzene emissions regulations came out. That was in 1999, July 1. So with that, they wanted to cap aromatics emission, total aromatics emissions to 1994 levels. So those have stayed. But what you'll see here, the blue is the benzene. So there was a dramatic drop in 1999 when it dropped down to 1%. What you'll see here is on the right is kind of a rural versus urban. So there's a lot more gasoline use in the urban area. So you can see benzene was quite high and then dramatically dropped after 1999. One thing you'll notice, though, these benzene levels, they actually drop probably a year or two before the benzene regulations kick in. And that's because regulations and laws usually take some time for producers to accommodate. So Environment Canada is not going to send a memo to the refineries, hey, tomorrow, guys, we're cutting the benzene emissions in half. A lot of these changes require long drawn out processes and significant investments at refineries to kind of bring these things down. Without getting into the nuts and bolts of refining, it's kind of hard to explain how some of how costly some of these changes are. I wish I could get into that a little bit, but another thing, sorry, the graph on the right is an illustration of actual benzene concentrations within the environment, not just aromatics and benzene within the gasoline. These are actually physical tests of atmospheric benzene. So you can see it actually did come down quite a bit after 1999, or actually even before, as refiners and producers were kind of bracing for those changes. Gasoline regulation. So the continual downward trend of sulfur in on-road vehicles has had the biggest impact on reducing vehicular emissions and pollution. You know, we hear of sulfur emissions, and we're, you know, okay, we're lowering sulfur in fuel. Is that going to lower sulfur emissions? Well, it's not just sulfur emissions that we're worried about. Sulfur actually poisons some catalytic converters and impairs the effectiveness of emission control systems within vehicles. So getting that sulfur down is actually assisting in all emissions. So we're not just worried about, you know, sulfur dioxide and things like that, right? So the EPA's Tier 2 gasoline sulfur program really kind of spurred this in North America. They did kind of borrow this. It actually started in Europe, but the way Canada works, we kind of model ourselves after what's happening in the States. So changes in North America really kind of came into effect with the Tier 2 gasoline sulfur program. So this is a program. They didn't just go to refiners and say, hey, let's lower emissions, let's lower sulfur, we're going to do this. No, they actually had GM, they had GM, Ford, Chrysler. They had all the major domestic car producers working on this as well. And you can see the dramatic drop in sulfur in this figure from the Canadian Fuels Association. So there's a couple of take homes here. So what the EPA is stating now is that vehicles meeting the Tier 2 emission standards from 20 years ago are now 77 to 95% cleaner than earlier models. The Canadian Fuels Association is making a similar statement saying cars nowadays compared to or have a 90% reduction in total emissions compared to models 30 years ago. So just kind of stressing that sulfur, we're not just looking at sulfur dioxide here, we're looking at total emissions, and that has to do with emission control systems. Diesel. So composed of light and heavy distillate cuts. If you can remember from the first slide, there's light, heavy distillate cuts, there's kerosene cuts. Those are all distillate cuts. Those are terms that are just kind of used generically, so don't get bogged down with what distillate actually is. Compared to gasoline, it is heavier, it's less volatile, it has a higher energy density. So as you can imagine, if you want to move something bigger, you want more power, you're gonna use diesel instead of gasoline. So this chart here is kind of compare and contrast. I wish the gasoline one was next to it, but I think you get the idea here that diesel, the energy density in diesel just allows it to be more suitable for moving heavy loads and creating more power. You know, that locomotives, farm equipment, buses, long haul trucks, things like that. Diesel, different types. So there's 3 sets of standards in accordance with the CGSB. So 3.517, that's just your regular diesel fuel, but there are 2 subtypes within that document. So type A, or number 1 diesel, as most people refer to it. Number 1 and number 2 monikers actually come from ASTM or American standards, where up here it's called type A or type B, but no one up here really calls it type A or type B. We still call it number 1 or number 2. So type A or number 1 diesel, it's a really light diesel. It's superior low temperature operability. I'm sorry, I put LTO here. I'm going to explain that in the upcoming slides. So low temperature operability is just how well the fuel is going to work in cold climates. And as you can imagine, in Canada, especially in Western Canada here, that's probably the biggest factor for us, or the biggest parameter that we worry about with diesel. So properties and specifications with type A do not vary throughout the year, only geographically. So number 1 diesel in northern BC would have superior low temp operability compared to, you know, southern Ontario. Number 2 diesel, or type B. So this is the diesel that we're used to. This is the diesel you would find at a pump or a station. This is the stuff you would put in your truck. So seasonal diesel, this is where properties are seasonally and geographically adjusted. So you'll hear the term summer diesel and winter diesel. It's not what we really call them, but there are differences throughout the year. Typically in the summer, you'll have diesel that's a little bit heavier, because those heavier molecules, those are the ones that we take out in the wintertime to prevent clouding and waxing, but more on that later. The next standard, CGSB 3.520, diesel fuel containing low levels of biodiesel. Very popular in Canada, and that's usually in the summertime. Again, we'll get into why that is later. Sorry, I'm getting a phone call. The joys of being a quality advisor, you are on call 24/7. All right, CGSB 3.522. This one is not very popular yet. A lot of OEMs don't want to see diesel above 5%, and there are also some blending constraints tied to that, and we'll get into that a little bit later here. Diesel key properties continued. Again, low temp operability is probably the most important one, but we'll start off with cetane number, because this is what I get most of the questions on. Cetane number, so it's a measure of the ignition quality of the diesel. Yeah, okay. So like I we learned earlier about what octane actually is. So that's the resistance of ignition upon compression. Well, what we want with diesel, we want it to light as fast as possible. So cetane number measures the delay between the start of the fuel injection into the combustion chamber and the beginning of the compression ignition. So as soon as that fuel gets injected, the quicker it ignites, combusts, the higher the cetane number. What some people kind of don't really understand here is it's not the compression of the fuel. It's actually the compression of the air in the chamber. It's already compressed usually by the time the diesel fuel is injected. So that's why you want that. You want that ignition right away. Cetane index. So this gets a lot of people confused, especially if they're looking at like a product certificate. So cetane index is not the cetane number. The cetane number is actually an engine test or a laptop combustion test, whereas the cetane index, so it's a calculated approximation of the cetane number. It uses only the density and the distillation points. So if you have a diesel with a cetane improver, it will not be accounted for using the cetane index. So a lot of people get confused between the index and number. Again, index is just an approximation, and sometimes it is not very accurate at all, but it does come in handy if you're, say, a refiner or producer and you know what your cetane number is and you don't want to run an engine test on every single blend kind of thing. So why is it important? Diesel engines run on compression ignition. So fuel must be able to auto-ignite. Higher cetane number is generally associated with improved cold starting, reduction in smoke, particulates, and running noise. I did find a couple of papers. I didn't want to put anything in here because I found some conflicting information on what a high cetane number will actually do in terms of mileage and power. The general consensus is doesn't help a lot, but there are a couple of papers out there that are saying it does. Just leave that at that. The specification, the CDSB minimum specification for cetane number is 40. Most diesels will meet 40 on their own without cetane improver additive, but some of the lighter diesels will need a bit of a boost there, and some refiners actually add a product right at the refinery to increase the cetane number. Okay, low temp operability. So this is probably the most important diesel parameter, especially in Canada. As you know, some industries, wintertime is actually probably the busiest time. So we do have a high demand for diesel throughout the year. But with that in mind, we have to carefully tailor the product to be able to meet geographical constraints. So low temperature operability, how we determine that 9 times out of 10 is cloud point. It's a really quick and easy test. It's the temperature at which the smallest observable crystals first appear. So we'll cool a diesel and watch it. And as soon as crystals start forming, that's the cloud point. So you do not want to be using a diesel past the cloud point, because what's going to happen is these little paraffin crystals that are forming, they're going to start blocking your filters, especially fine filters. It can even start building up in distribution lines, things like that. So usually the end result is your engine starving of fuel. Low temp operability can also be determined using other test methods, so such as cold filter plugging point or low temperature flow test. So that's basically where they're chilling the sample as hard and fast, pretty hard and fast, and then you're dumping it through a screen and timing it. So it is a measure kind of crystallization as well as viscosity, because viscosity is crucial in low temperatures for sure. What is the specifications? Cloud point specifications are based on the 2.5% low end design temperature over half-month periods for area of intended use. So basically, we have 30 years of data from Environment Canada weather stations throughout the country that give us the approximate temperatures for areas. It's hard to explain, so I'll show you a little bit more, a better kind of a picture of this. So what we have on the left here is a cloud point schedule. So refiners, terminals, things like that, we all have to meet these specifications. So earlier in the slide when we said for half month periods, so basically every half month it will change. Obviously see down there in December, it did not change. So And then on the right, we have a CloudPoint map that goes along with this CloudPoint schedule. And what I would like to show you here next is kind of a blow up of the CloudPoint map. So back here, you see at the very top of this table, you see BC02, BC03, and those correspond to geographical areas in BC here. What I'd like to kind of illustrate here is the geographical areas are put together based on similarities in climate. So we have BC01, which is basically a coastal climate. You have BC02, southern BC, mainland BC03, and it kind of works its way up north. So we have our production hub here in Edmonton. So the way we kind of work this out in BC, we have a terminal in Nanaimo and Vancouver. We would send product that would meet BC01 specifications to that terminal. We share a terminal with IOL and Shell down in Kamloops. We share the terminal. So we would basically be sending all the refiners up in Edmonton would be sending stuff to Kamloops that meets the BC02 requirement. Well, there's also a terminal in Prince George and one in Terrace. We would send product from Edmonton to those areas to meet BC03. Up in BC04, you start getting into these rural areas up north. We're not going to have big terminals. We're going to have maybe some card locks and kind of a bulk fuel station or terminal. So we'll basically rail product directly up north or truck it. Diesel key properties, density. So obviously the weight per unit of volume of fuel. Knowledge of density of a batch of fuel is useful for someone receiving the fuel. If the density of the fuel received is significantly different, then we know there's probably some kind of contamination. But why? I always get the question why we pick 15 degrees Celsius. Well, it's kind of a chosen reference temperature, and it's basically to align with long established international standards and trading practices. So again, why is it important? It's used for QA/QC. It's a really quick test to do, really quick result that'll tell you if there's some kind of contamination. But then for accounting purposes, we have to account for the expansion and contraction of gasoline and diesel. I probably should have put this in here, but just a rule of thumb, for every 8 degrees of change, the volume of gasoline will change by 1%. And then with diesel, I think it's every 12 degrees, you get a 1% change. So when I've had questions before where we've sold the diesel in Edmonton and it's, let's say it's compensated. So say we sell it, it's -10 here, and a few weeks later it's in someone's tank and it's -30. They will notice a drop in volume. So we do have to account for those things. Viscosity, I see I'm running a little bit long here, so I'm going to start going a little bit quicker here. Viscosity, a measurement of liquids' resistance to deformation or flow. Fuel with the wrong viscosity can cause engine or fuel system damage as it affects the atomization. In a diesel engine, you need a finely controlled spray pattern to help with the combustion. So high viscosity will increase gear train, cam, and follower wear on fuel pump assemblies. Low viscosity fuel may not provide adequate lubrication to plungers, barrels, injectors. Specifications, type 1 diesel, again, that does not change. Type 2 diesel, the lower viscosity is allowed when temperatures drop. So in the winter, we're allowed a lower viscosity, as you can imagine, under ambient temperature. If it's cold, then the viscosity is going to drop. So. Diesel additives, conductivity, an important one, reduces the ability to accumulate static charge, reducing the risk of sparking or fires through handling. Lubricity, lubricates fuel injector pumps within the diesel fuel engine. Ultra low sulfur diesel has poor lubricating properties due to large reduction in sulfur. Sulfur back in the day, before it was ultra low sulfur, did not require lubricity additives. It does now. And they believe that is because sulfur doesn't act as a lubricant in itself, but it would form a special alloy with nickel in metal in engines. so it would form some kind of eutectic low point lubricant, or low melting point lubricant. So nowadays, with sulfur being like, geez, the ppm limit is 15 ppm, but often refiners are producing, you know, almost sulfur-free diesel. So lubricity additive is basically needed in all ULSD. Cetane improver improves the cetane. Not widely used. Sometimes it's needed. Deposit control additive. This is kind of new in diesel. You'll see these at some of the retail stations calling it premium diesel. It's essentially a deposit control additive and a little bit of cetane improver added to your diesel. Antifreeze added in the winter cold temperatures to help keep dissolved water dispersed throughout the fuel. Biggest use I know of it. It is dumped in rail cars. We'll put like a few liters in. And what it'll do is it'll prevent the icing up of rail cars, so we don't have to burst through ice to drain them out. Again, red dye used in diesel just as it is in gasoline. Diesel regulatory limits. Really, the biggest concern at ECCC is sulfur in diesel. In 2006, it was capped at 15 ppm. Now, nearly all diesel offerings are ULSD. There is an off-road, a locomotive standard where you can still use 500 ppm sulfur in diesel, but since, you know, refiners, 99% of it is for on-road use, all diesel is essentially low sulfur now. Other fuel products. Okay, heating fuel, furnace oil. I believe there's 6 different types. That's just a middle distillate that's used for burning and heating. Marine diesel, marine gas oil, very similar to diesel. You're allowed a little bit higher sulfur in it, and high flash point requirements. That's right. High flash point requirements because a lot of these engines are actually inside or in an elevated, inside of a room that has elevated temperatures. And flash point, I guess I should have included that into my diesel properties. That's just basically where a fuel, the temperature at which the fuel will ignite if there's a spark in the area. Aviation jet fuel, didn't have a lot of time to get into this. This is kind of my wheelhouse, is aviation jet fuel, just a light diesel fuel with stringent specifications. Our Canadian specifications are aligned with international aviation specs like ASTM, EIJIG. As you can imagine, an international set of standards is kind of required for aviation fuel. Propane LPG, there are 2 grades. One is for vehicle use. I don't think we see propane vehicles out there anymore, but and then grade 2, that's basically your regular propane that you would use in your barbecue. Okay, we'll get through this pretty quickly here. We're getting into renewable fuels. Just wanted to touch on carbon intensity just very quickly because that's going to be mentioned in here. What you can see here is diesel is pretty high. Gasoline, conventional diesel are pretty high. Ethanol is a lot lower. So are your biofuels. The reason ethanol and biodiesel are a lot lower is because they take into account the CO2 that they're pulling from the air while those objects while the feedstock is still alive, let's say. So if we're using ethanol from grains, those plants are pulling CO2 out of the air while they're alive. So that's what we call from well to wheels in terms of carbon intensity. Ethanol, alcohol derived from feedstock containing large amounts of sugar. In Canada, it's principally sourced from corn and wheat. It can be burned in nearly pure form in modified engines, but the most common blend is E10. That ethanol that goes into gasoline is actually denatured, means there's an additive put into it to make it unfit for consumption. For automotive use, that's right, the denaturant in ethanol for ethanolized gasoline is actually gasoline. Ethanol specifications, there are 2 sets. There's one for, just ethanol in itself. There are 2 sets. There's CGSB standard for the ethanol that we put into gasoline. And then there's another one that we basically would burn straight or put a little bit of gasoline into, but 3.516 is basically what we work with. This 3.512, not very popular. Just looking at this figure at the bottom, this kind of highlights what ethanol does. I got that in the next slide. So we'll produce something called RBOB at the refinery, so base for oxygenated blend or before oxygenated blending. So that'll have like an 84 octane. Ethanol will add about 3 to 4 octane numbers. And then here we got an SBOB or PBOB, so that's a supreme or premium base for oxygenated blending. We will add ethanol to that, and boom, that's where you get your 94 octane from. So when you see a 93 or 94 octane offering at a retail pump, that is going to be premium with ethanol added. Benefits of ethanol gasoline: increases octane rating for more complete burning of fuel, lowers emissions, lowers overall fuel and carbon intensity. Some of the drawbacks: it actually does contain less energy per volume of gas or per unit volume of gasoline, and it does decrease mileage. But the overall carbon intensity of that overcomes the drop in mileage, where the overall fuel CI is still a net improvement. Ethanol does increase gasoline RVP, so we have to be mindful of that while we're producing gasoline prior to ethanol addition. What happens at a refinery, we will basically blend a whole bunch of BOB and SBOB, and then we add the ethanol at the rack as it's going into trucks. Because ethanol is hydrophilic and it limits the distribution option. So we can't really move it by rail or pipeline right now, because that will cause corrosion. The pipelines will also pick up debris and things like that. Ethanol mandates in Canada, 5% federally. Manitoba right now is 9.25. That will be going up to 10% in 2022. Currently, Saskatchewan is at 7.5%. We can easily meet things like 7.5% by making sure all 87 octane is blended E10. Next up, renewable fuels, biodiesel. B100 or FAME. It's a fuel comprised of monoalkyl esters of long chain fatty acids. It's a better slide coming up on that. The CI of the carbon intensity of FAME is dependent on the feedstock. The benefits of B100: it's the lowest carbon intensity fuel, and it's got great lubrication properties. So once we start blending biodiesel into diesel, we no longer need that lubricity additive. Typically, biodiesel is blended at 5%, so it's called a B5 blend. Some of the drawbacks of using FAME or B100: poor low temp operability. This stuff will cloud up even at like plus 10. I think I've seen some tallow. Tallow is basically an animal fat based feedstock. It's got poor stability, so it does usually require additized stability additives. It too is hydrophilic, and it is a good solvent. So again, pushing this through pipelines, it doesn't really happen. We're going to try it here pretty soon in Alberta, but it's kind of a no-no. Everything with bio and HRD will be the next slide. Renewable diesels. A lot of this stuff is still new to industry. So, you know, the first person to start pushing it through a pipeline may start experiencing some setbacks. So these things they're vetted, and people kind of just wait and sit and wait. Hopefully someone else tries it. But so typically we use soy or canola based biodiesel in Canada, and there's just a quick table that kind of shows us CT number and stability increase, your cold flow properties drop. So you can see, okay, we got coconut, palm, beef, tallow. And a lot of that is really dependent on the saturation of the fats in there. So just a quick overview of how B100 is made. So you got your triglycerides on the left. You see these ester groups. I'm sorry, I'm a chemist. That's just the oxygen in there bound. So what you're left with is these methyl esters. They cloud up really easily. Again, they're not very stable. Mainly because of these oxygen groups. And then at the bottom, there is kind of the full life cycle of the process. It does take alcohol and glycerol to produce. The biodiesel mandate, some jurisdictions, it's based on carbon intensity rather than just FAME content, because again, the CI of the FAME or the B100 is highly dependent on the feedstock. So that's why the government's not just like, hey, just put 2% in here and you're going to be fine. Okay, well, if I put 2% of a high CI diesel, really, what am I saving here? Hydrotreated renewable diesel, this is kind of the second generation of fuel. It's also referred to as hydrogenated vegetable oil, R100 or Neste. If you hear the word Neste, that's just one of the biggest producers. It's got lower carbon intensity than regular diesel, a high cetane number, excellent stability, and a high blend percentage. So whereas FAME is limited to about B5, we can put really high percentages of HRD into fuel. The drawbacks, low density, so lower mileage, poor lubricity. It's very, very expensive, and it can cause corrosion issues. So often additives are needed to combat that. Biodiesel and HRD, hydrotreated renewable diesel, come from the same feedstock. So if you look at again, we got a triglyceride here, but then the HRD, you're not seeing that ester group, you're not seeing any oxygen. This is a saturated paraffin, so straight chain hydrocarbon, high in cetane, great properties for blending into existing diesel. Review of renewable manufacturing process. So just to kind of illustrate, the feedstocks for both of these products are the same. The processing is different. Transesterification is kind of a chemical process, kind of just tied to biodiesel, whereas hydrotreating, that's basically a refining process that happens with regular diesel. It can be costly, and you can kind of order your boutique HRD if you have the kind of money it requires. Just a quick comparison, diesel versus FAME versus HRD, regular diesel down here, biodiesel here, renewable diesel here. Things to note here is the low density of renewable diesel, the inferior low temp operability of biodiesel, better with HRD. And down here at the bottom, lubricity, good on diesel, excellent for biodiesel. It's not really good for renewable diesel. I got to change that to bad. Considerations, this is just kind of a general table of some properties of ethanol, biodiesel, and renewable HRD. Again, a blending season for ethanol year round. I could have done a full presentation on either one of these products. Blending season and biodiesel, sorry, I didn't get into this really, due to the low temp operability in Canada, really, we only blended from April 1 to September 30. There are some blend walls up to 10% basically with ethanol. Some people are trying to push 15. I think the Ontario government's looking into that for the future. Right now, FAME about 5%, and then HRD up to 30%. We actually do have some customers that are using 100% HRD, and everything seems to be just fine. Sorry, I had to pedal to the metal on the last few slides there. So sorry about that, everyone. Any questions?
Oh, great. We do have one question that's on here right now. If anyone else has any questions, definitely you can type into the Q&A or the chat area. Alex is asking, aftermarket diesel additives are very common and in some cases recommended by engine manufacturers. What is the viewpoint from the fuel refiners?
That's a really great question. We do not advocate for the use of aftermarket fuels. One, because our products should meet end user requirements at the terminal. We do realize that some things happen, contamination, sitting in a tank somewhere, a little bit extra water, but we do not advocate the use of aftermarket additives. And again, I talked about it earlier in the presentation. The additives that we use as producers, they are run through a battery of tests, and we know exactly what they're going to do to our fuel. Whereas if you're just buying a jar of something off of a shelf and dumping it into the fuel, we don't know what that additive is going to do to our fuel. There are instances where it could drop the performance of your fuel, but since we don't have a lot of control, we don't have a lot of knowledge about it, we do not advocate for it.
No, that's fair. Here's a question. If ethanol in gasoline increases from 10 to 15%, does that pose problems for fuel system components / materials?
It shouldn't in terms of corrosion and metal and things like that, because ethanol itself will have corrosion specifications. So it has to meet those specifications, and so does the gasoline it's getting blended with. What I would be worried about is probably more gaskets, rubbers, and things like that. I don't see 15% being a big issue when it comes to that stuff, but there are other considerations, like outboard motors, cold temperatures. I really wish I could have got into the science ethanol blending, because one thing that kind of restricts its use is really cold temperatures. So up in like Northwest Territories and things like that, you got to start worrying about phase separation, the ability for ethanolized gasoline to hold water. But when it comes to E15, it's obviously going to pull in a lot more water, but I would be more worried about, rubbers, any kind of polymerized gaskets. Like when we see, imagine it's using gasoline that's conventional, and all of a sudden it's exposed to 15% ethanol. There's definitely a chemical change in the product. But right now, we haven't heard of any major roadblocks to 15%, other than kind of OEM hesitation. Not really a defined problem, not a specific one.
Okay. I don't see any other questions right now. I'll give it another little bit here. But I do want to thank you so much, Kyle, for presenting. This was actually a really good presentation. And I know you're very knowledgeable, that I feel like we could definitely have you back and talk on some more of this. So
yeah, it's aptly called just fuel quality 101. Because like I said, we could go into the weeds in a lot of these slides, and especially when it comes to renewable diesel blending or ethanol blending, because there are always a lot of questions and things of that nature.
no problem. Okay, so I don't see anything else. If there is questions from anybody, definitely feel free to contact STL Alberta, and we will definitely forward them over to Kyle. I'd like to thank everyone for attending. I'd like to acknowledge SAE as well, who's been partnering with us this season. Yeah, any questions, please contact us.
Absolutely. Thanks, everyone.
Thank you.
Thanks, Kyle.